Okay, I want to derive for you something called Pascal's triangle, and we're going to do it by looking at these different powers of the binomial x plus y. So x plus y to the 0, that is by definition 1. So all we do is accept that. It's a definition. X plus y to the first power is x plus y. X plus y squared is going to be x squared plus 2xy plus y squared, and we find that by just multiplying x plus y times x plus y. Now I'll tell you that x plus y to the third power is x cubed plus 3x squared y, 3xy squared plus y cubed. Now how do we get this? Well, we get it by multiplying just like we found this right here, except that to get this, we're going to multiply x plus y times x plus y squared. So when I do that, x plus y squared is x squared plus 2xy plus y squared. And I want to multiply that by x plus y. So let's start by x times x is x cubed. So you can see where that first x cubed term comes from. X times 2x squared is going to be 2x squared y. X times y squared is going to be x y squared. Now I move to the y times x squared y. I'll write it underneath the term it's similar to. And then y times 2xy is going to be 2x y squared. And then y times y squared is going to be y cubed. So when I use my regular long multiplication like this, now I'll add in columns where I have my similar terms. I get x cubed plus 3x squared y plus 3xy squared plus y cubed. So you can see that this that we get right here matches exactly what I put over here. So here's a justification for why this looks this way. Now what I want to do is with our inductive reasoning is just fill in the next row here without having to go through this long multiplication process. So if I ask you what x plus y to the fourth power is, and I say, well, for instance, just give me the first term, you're going to look at this pattern here with these exponents and say it's going to be x to the fourth. Then it's going to be something times, here is x squared y, this goes x cubed, x squared, x, no x, or x to the 0 power. So if this goes x to the fourth, this is going to be x cubed, y. The next one is going to be plus x squared, y to the second, plus something times x, y to the third, plus y to the fourth power. The last term will be y to the fourth power, just like the last term here was y to the third power. So how do I fill in these coefficients? That's the question. The exponents are easy. If I look at these exponents, I'll put ones in where you don't see them, the sum of the exponents on any one term always adds up to this exponent right here. And they go in decreasing powers for x and increasing powers for y. So what do I put here for the coefficients? To see that, we have to get what's called Pascal's triangle. I'll go up here and fill in all the coefficients that we don't see. And it looks like this. Okay, so for these first 3 or 4 rows right here, if I take out all the variables and just write down the coefficients, what do I end up with? Well, I have 1, 1, 1, 1, 1, 1, no variables, then 1, 2, 1, and then 1, 3, 3, 1. So can you fill in the next row? Do you see this pattern right here, this two-dimensional pattern? So if you look closely, what you'll see is that you add these two to get this one. You add these two to get this one. You add these two to get this one. It always starts with a 1, so I'm going to get a 1. I'll add these two to get this one. I'll add these two to get this one, those two, and then it ends in a 1. So my coefficients right here for this line happen to be 4, 1, 4, 6, 4, 1. And that's exactly what you'll get if you multiply x plus y times x plus y times x plus y times x plus y. So this right here is called Pascal's triangle, and it's what we use to find these coefficients in this binomial expansion. Now I want to go to the next board and just show you real quickly a relationship between Pascal's triangle and the Fibonacci sequence. So here I've written Pascal's triangle again. Here's a little postage stamp with Pascal on it. This postage stamp is to recognize his birth in the 1623. And then also here is a postage stamp from Liberia with Pascal's triangle in Chinese from the year 1303. So here we have somebody working with Pascal's triangle before it was actually called Pascal's triangle. Anyways. So let's see, here's Pascal's triangle. Can we fill in the next row here using our inductive reasoning now that we know what the pattern is? Always starts with the 1, add these two to get the next one, 5, 10, 10, 5, 1. So that's what we would use to expand x plus y to the 5th power. Now let me show you the connection between this and the Fibonacci sequence. To do that, what I'm going to do is take Pascal's triangle and just write it all over here like flush left. So it'll be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. And just keep going like that. And now I'm going to add up the diagonals. Up that diagonal, 1. Up that diagonal, 1. Up this diagonal, 2. This diagonal, 3. Up this diagonal, 1 plus 3 is 4 and 1 is 5. If I was to write the next row down here, 1, 5, 10, 10, 5, 1, and go up that diagonal, what do you think I would get? 1 plus 4 plus 3, 8. And you can see right here, Fibonacci sequence. The farther down you go here, the more and more numbers you get in the Fibonacci sequence by adding up these columns in Pascal's triangle when it's written over this way, flush left. So again, that's something that drew me to mathematics in the first place. I'd see a couple things that seem at first to be completely unrelated, like the Fibonacci sequence and Pascal's triangle, and then find out later on that there's actually a very close connection between the two things. So Fibonacci sequence, Pascal's triangle.